Okay, I think we can start. So, hello everyone. I'm Shohei Mori from Graz University of Technology, and welcome to the sixth paper session of USMA 2020, which is about projection mapping and 360 experiences. So, in this session, we have 5 presentations, and starting from Ilamov projection, deforming of 3D shape by dynamic projection mapping, presented by Kentaro Fukumizu, Ryu Miyashita, Satoshi Ishikawa. So, Kentaro, please. Yes.
So please play the movie. Kentaro Fukumizu is a graduate student of the University of Tokyo. I will start my presentation with the title shown. We propose an application in which a rigid project appears to be defined by projection modeling. Both there is a 3D object as a projection target as shown in the example. It is rigid, so it will not deform by shaking. However, the image in the farthest corner in video makes the target appear to have elasticity. It is possible to specify the degree of elasticity for each location by using elasticity map as the bottom left. Principle this illusion used in study is a perceptual property discovered by Levinson et al. This states that when we recognize a moving object, we recognize its color, shape, and motion in separate channels in the brain, and these channels are integrated in the higher order areas of vision. There are some researches that make good use of this principle, which is called derivation maps or makeup maps. They are not being referred. Projector is responsible for bringing information and deformation to their message regions even in limited resolution. We briefly describe dynamic projection of DPM which is used in the title of our research. The dynamic has mainly two means that the projection image can be replaced or that projection image sticks tightly on the moving object. Here we discuss the later one. In DPM, a high-speed camera is used for sensing such as tracking barcodes. Then the tracked information is transformed into the coordinate system of the projector, and the projection image is rendered and projected. The usual 120 fps or so projectors cause geometric delays, and observer feels image seems to follow with a delay, but by turning the thread at 100 fps, the delay from imaging to projection is replaceable. There appears no big delay to the observer. This section explains the comparison between our method and previous methods. First of all, as for the projection target, compared to the 3D, 2D, or 3D static plane on the emulation labs, we use 3D moving solid, same as in makeup labs. In addition, it is necessary to generate the image for projection in real time. In previous researches, it is rendered based on the animations prepared in advance. Compared to these methods, our method uses the information of the interior of the target, so the shape of the deformed object can only be revealed through physical simulation. Therefore, a fast physics simulation method is needed to avoid noticeable misalignment due to delay. Now, I will give an outline of the proposed method. In this study, we mainly use the flow shown in this figure. First, 2 high-speed cameras are used to capture the images of the target. The information from the infrared camera is used to track the 3D position and rotation, and the information from the digital light camera is used to estimate the environmental light rate. This information is transferred to the GPU, and the first image is rendered based on the geometry before it is deformed. Next, the geometry is deformed using the first rendered image. Finally, the projection image is rendered based on the deformed geometry. To realize the application of this research, there are 3 main contributions of proposed method. First, if the projection image extends out to the target, the audience will notice projection as the quality of experience will decrease. Therefore, we propose an algorithm where the projection image never extends out of the target, and that is enough fast for DPM. Next, all systems rendered based on the result of the calculation create a contribution. In this study, we not only naturally extend the algorithm of deformation lamps to 3D solid, but also add the down to emphasize the 3D effect to make the illusion appear more effective. Finally, our image generation algorithm takes into account the contribution of environmental lighting. This guarantees robust quality illusion in environments where the lighting changing over time, such as party or concert halls. We use triangular point mesh as a data structure of 3D model of the lighting. We will explain how to develop a point mesh by creating the portions of vertices. This research, we use GPU to perform the deformation process to increase the speed, so an algorithm where each vertex is deformed independently is preferred. Furthermore, if the projection image extends out of the target, the quality of the experience will be degraded, so it is necessary to prevent it. Therefore, we extend the shape matching method, which can calculate elastic bodies in high speed. The shape matching method assumes that the virtual vertex, which is one of the elastic body, is connected by a single spring to the real vertex, which is one of the rigid body to which the virtual vertex will eventually converge. This is an extension of shape matching method in grade. First, here's the update. We suppose that the previous virtual vertex and corresponding nearest real vertex and the white silhouette of the target are in this positional relationship. The shape matching method is applied without extension when the previous virtual vertex are too far out of the silhouette. US virtual vertex can extend out the silhouette after the update. Therefore, we inject a process of mapping the virtual vertex to the nearest controller before applying the equation of motion. This enables virtual vertex not to extend out while maintaining a smooth distribution of vertex near the controller. Finally, it is useful to be able to specify the strength of elasticity for each vertex. We realize it by creating the corresponding texture based on the UV coordinate of the target polygon. We call this the elasticity map. In this example, the left half of the face is painted blue, and the virtual vertex in this region is almost fixed to the real vertex. On the other hand, the right half of the face is painted red, and those in this area have strong elasticity. Next, we describe how to render the projection image to give the illusion. Rest the final luminance should be observed by the audience PB. Then P projection strength P is decided by incorporating information such as environmental light and reflectance as follows. Then, we naturally extend this equation to see object. Using a simple Lambatian model, the linear product of the normal and the projector direction is used to obtain the equation shown in the red box. Moreover, in this study, we add a term for shading with term as shown in the blue box to emphasize the 3D effect. Next, let's take a look at the projection result. This demo shows the result with various elasticity maps. By projecting the image in the upper corner, our system gives the illusion of elasticity even though the object is made of hard plaster. You can use elasticity map at the bottom left to specify various regions to be deformed. Next, here are results of projections with various degrees of elasticity. In our system, normal strength of elasticity is expressed as a spring constant, so various elasticities can be expressed by changing the spring constant. When K is 1.0, the motion is quite large, but when K is 5.0, it's large. The following are the result of projections under various environmental lighting conditions. In this demo, we are projecting the blue light with the blue light off and on. As explained in the proposed method, the contribution of the environmental lighting is estimated in real time, so it is possible to keep the illusion even if it changes dynamically. This section describes how to evaluate the delay time of the system. The right figure shows the image generation process, and the right one shows the processing time for solving the lighting equation. Subtracting the time for sensing and projection, DPM is possible when the entire image generation process is less than 2 milliseconds. Based on this result, we found that up to 500 we keep to a certain extent low for dynamic estimation. Using a low polygon model can reduce the delay, but there is a trade-off with the projection quality. We think it is important to find out how many details is required to maintain the selective quality. Finally, we conclude our presentation. First, we propose the L1 projection system, which generates an illusion of deformation in the geometry of the projection target. Next, we evaluate the performance of our system and examine the number of batches for which the throughput is enough fast to satisfy the requirements of DPM. Plus, we plan to conduct an experiment for evaluating the effectiveness of our method. Thank you for listening.
Okay, thank you for the presentation. The results look pretty impressive, I would say. So, do you have any questions from the audience? I don't see any questions so far in Hoover, but probably you can have a question directly through your microphone here. Okay, if not, I have some questions. Can you hear me, Kentaro, now?
Okay, can you hear me?
Yeah, yes. So let me have a question. So I would like to know the scalability of the system, because I suppose you currently have results of one object of a head replica of a lady. So if the user wants to use your system and introduce a new object, for example, what would be the most challenging part to use your system or to implement your system?
It's for implementation for other objects because it's very simple algorithm for human face. So extend for like water.
Sorry, I think I missed that. Could you repeat that again?
Sorry, I can't hear.
Oh, okay. Some microphone issues happening again, I guess. What about now? You still have 2 minutes, I think. Hello, Kentaro?
Hello? Can you hear me?
Yes, yes. So could you repeat the answer again? Because I think we couldn't hear you.
I can hear you, but it speak a little slow.
Okay, so probably you can answer that in the public chat, or probably later I can post my question on the QA of the FUBA, maybe.
Oh, okay.
Oh, yeah, so now you can hear me.
Oh, yeah, now.
Okay, so could you answer the question again?
So I can't hear. So repeat.
So okay, so I can ask you again my question. So I simply would like to know the scalability of your system, right? So because you are currently showing only one object applied, and so
projection target.
Yes, exactly. So let's say, so if somebody wants to use your system, and what would be the most difficult part or challenging part?
The correspondence of real projection target and 3D model for rendering is very hard problem. So create this target for 3D printing is a very hard problem.
Okay. So thanks again, presenter. We are short in time, so let's move on to the next presentation. Thank you, Kentaro. Yes, so Next presentation will be about real-time adaptive color correction in dynamic projection mapping, presented by Philip Kulth, Vanessa Lange, Mark Staminger, Frank Bauer. And so, yeah, Philip, please go ahead.
Hello and welcome to my presentation, this year in the Home Office edition. As you can see from the title, we are in the context of projection mapping now, and therefore I would like to give a very brief introduction to this topic. In projection mapping, we have a target object of arbitrary shape. This is tracked, in our case, by a depth camera. Lastly, we have one or more projectors targeting the object with the goal of changing its appearance. Using these also, thanks to our tracking, we can move the object around and the projection follows. In the past, for example, we built a small painting application on top of this system. This allows us to change the object's apparent material interactively. Lastly, here we give the impression of a glossy material, which reflects the surrounding. This is achieved by capturing the scene with a mirror ball. Again, keep in mind that all you see here is real video captured by a real camera. This is not rendered. Our system is geometrically calibrated in an offline step. The object is tracked in real time. The important factor missing from the setup is correct color reproduction. The final color is influenced by a lot of factors, the most important ones being the projector response. So given an input RGB, what color does it project? The environment lighting present in the room, and the surface color. Our objects are usually white-ish, but not perfectly so. Our system is an attempt to solve for all these unknowns during runtime. We don't require an offline color calibration. This allows us to react to changing conditions, like for example, changing environment light. We therefore use a color sensor which observes the projection and adapts it if necessary. While our projection mapping can support multiple projectors, this work focuses on the single projector case. So in projection mapping, we usually have some target appearance which we want to achieve. Now, if the projector displays its image, the resulting camera image may look different due to the factors discussed earlier. Our system then takes samples in regular intervals and feeds them to a solver which estimates these factors. We then construct a color gamut per surface point and bring the target appearance into this projector's displayable range. This is done smoothly in order to avoid edges. Using these estimated parameters, we can adapt the projection, which leads to a camera image closer to the target appearance. These steps are repeated over time, such that our system can react to changing conditions. Our color transport formulation is as follows. On the left, we have the color the camera records. This is influenced, of course, by the color sent to the projector. This gets modulated by the surface orientation, assuming a diffuse surface. T is our projector response. In accordance with the literature, we model this with the second order polynomial. Lastly, we have E, our environment light. In this formulation, it is influenced by the surface orientation, but we discussed this now more. There's no surface color in this formulation. We address this later. So I already showed you this video where we used a mirror ball. This could also be used to reconstruct an irradiance map to estimate the incoming environment light. We would like something similar, but without the physical mirror ball. Also, we would like something more local, not a single irradiance probe per scene. We now distribute virtual irradiance probes in our scene, which are solved for by our solving step. These are able to capture more spatially varying environment light. The probes are modeled by spherical harmonics and are interpolated over the surface. Because we solve in regular time intervals, we can update our estimate of the environment light during runtime, and therefore react to changes. As for the projector response, this also comes out of the solver. Here you see me adding a sample, which causes our estimate of the projector response and gamut to update. Of course, in a real setup, the sampling happens automatically and regularly. Here we take samples from the whole image and use them to reconstruct a response for the whole projector. We will now talk about how we refine this response locally in order to capture more spatially varying effects. Okay, so far our projector response is global for the whole projector. Also, while our environment light estimate has these local components with our irradiance probes, we cannot capture sharp edges or small effects with this approach. We therefore refine the global model in each frame locally. On the left side of this formula, you can see again the color as currently captured by the color camera. C prime is the color as predicted by our original color transport formulation in the top right. If there is a difference between the two, something apparently is wrong for a given surface point. We separate these local variations into multiplicative effects, such as the surface color or vignetting, and additive ones, such as environment light and interreflectance. These factors are solved for in a compute shader in each frame for each pixel. However, since these are two unknowns and only one equation, we solve for the factors in screen space tiles, which are jittered each frame and temporally smoothed. This is not quite per pixel, but allows for much finer effect estimation than our previous steps. Here you see a side-by-side comparison between the environment light estimation without and with the refinement. We placed an artificial strong red and blue environment light with a sharp edge in the scene. Light probes alone cannot capture this, but the refinement can reconstruct an edge. Note that the top right image is for visualization purposes only. The system sees only the top left image. Lastly, for gamut mapping, we construct the surface of the gamut for points on the target object. Ideally, we would like to construct a gamut for each surface point, but this is infeasible due to computational speed. We therefore again place probes on the object surface at which we evaluate the gamut. The gamuts are then interpolated over the surface to yield a per pixel gamut. The interpolation takes into account that in between the samples, we don't have knowledge about the displayable colors. The interpolation therefore defines a region between the samples where we map to a conservative gamut, so the intersection of all surrounding gamuts. Since gamut mapping often takes the shape of a ray cast against the gamut surface, we represent the gamut as a time distance function, as is done in the literature. This also makes interpolating between differently shaped gamuts trivial. So I talked a lot about how we take samples of the projector and camera image in regular time intervals. I would like to go into a little more detail here. Of course, if we only take samples in one frame, this restricts the samples we have for solving. Our goal is therefore to sample as much of the RGB space as possible over time. Also, we would like to stay adaptive to changes in the conditions, so samples must become invalid eventually or be updated. And of course, the number of samples should not explode over time, so simply adding new ones is infeasible. For solving, we need each sample to hold the projector and camera RGB values for the 3D position on the object surface and the normal vector. Our solution is to subdivide the RGB space into buckets. The same is done for the 3D position and the normal. For each of these buckets, we store only one camera RGB value. The buckets also store the confidence in this value in the form of a variance between all captured values. This confidence is used in the solving step as a weighting factor. It also determines how fast the bucket's value adapts to the new, different value. Lastly, a few results. On the very left, we see the color we want to achieve. This example again has the red and blue environment light, which leads to an incorrect result. This is especially apparent in the top row. The third row is without gamut mapping, which introduces some clipping artifacts. Gamut mapping brings the image into the displayable range. The last two columns are the projector image before and after correction. That's it for my presentation. Thank you very much for listening.
Okay, thank you for the presentation. So let's move on to the Q&A session. Do you have any questions from the audience? Anybody? I'm currently checking the Hoover app, and yeah, I don't see any questions yet. Please don't forget to post your questions on Hoover or either on public chat. I mean, yes. So, okay, so I have a question. Can you hear me, Philip?
Yes, I can hear.
So I assume that when moving a target object in the scene, and if some occlusion happens in the geometry, and then the resultant image would flicker, I suppose. But did you observe such artifacts? And for example, how many samples do you need to stably estimate the lighting?
So we don't really see flickering when moving the object. Did I understand correctly? Question?
Mm-hmm.
I think that's because the sampling only takes like every like 100 milliseconds or something, and we smoothly interpolate between the previous points and the next one.
I see. Yeah.
So we always take samples from the whole image, both in camera and projector. So usually one of these sampling steps is enough to color correct the current image. But then, of course, this doesn't sample the whole RGB spectrum. So more samples is always better. So later projection frames always help. I hope this answered your second question.
So my second question was, how many samples do you need to stably or practically estimate the lighting?
The lighting. So usually just one frame. So this is then I think a couple of thousand samples because we take all pixels into account. But then of course more samples helps. That's what I meant.
Oh yeah. Mm-hmm. So still no questions from the audience? Okay, so maybe I can have some short questions. So if I understand it correctly, your solver needs to have the normal as sample, one of the samples. And can you apply your method for a complete plane object, like a screen?
We haven't tested it, but I would assume yes, because then.
So there's no matter if the normals have any variations.
I don't think so, because I guess we only use these samples which we already recorded, right? So we on a planar object, all the normals which point in the same direction, and it doesn't really matter if the solver like computes a wrong result for different normals. Then you understand?
Okay. Yeah, I think so. Yes. So any other questions from the audience? Still have 1 minute. Okay, so this is a kind of stupid question, I guess, but do you have any reasons why you don't have any comparisons to existing work, or is there any technical background of this?
So most work actually is not in real time. It doesn't compute this the whole thing in real time, so we didn't really have opportunity to compare. But I think the next talk is on the same subject, so I'm very interested in
Yes. Yes, exactly. Yes. Okay, thank you again for the presenter. We will move on to the next. Presentation. So the next presentation is a robust reflectance estimation for projection-based appearance control in a dynamic light environment. Presented by Ryo Akiyama, Toshiro Yamamoto, Toshiyuki Amano, Takefumi Taketomi, Alexander Platsky, Christian Sandor, and Hirokazu Kato. And this will be presented by Ryo. Please go ahead.
Hello everyone, thank you for coming to our presentation. I'm Ryo Akiyama from NTT Japan. Today, I will talk about our TBCZ paper named Robust Reflectance Estimation for Projection-Based Appearance Control. To control color of real objects by projection, we need to think about reflectance and environmental light. When the target surface is white and there is no environmental light, it is the easiest case. When we want to present orange color, the projector just need to project orange color. But however, when the surface has color or there is environmental light, the problem becomes complex. So the projection system needs to select projection color carefully based on reflectance and environmental light. There are many research which control appearance of real object by projection. We picked up some research here. All work here in reflectance estimation. When target appearance is known in advance, like projecting movie or pictures, robust reflectance estimation method is already proposed. However, when we want to edit appearance of real objects, like this work, the system cannot have target appearance in advance, and there is no method which can be applied in dynamic light environment. So our work is located here as a basic technology of projection-based appearance control research. First, I explained the conventional method to estimate reflectance. This method is creating projection system with one projector and one camera. And one camera capture C can be expressed with this equation. And in this equation, only reflectance K is unknown. So we can estimate reflectance K by using only this equation. However, this model does not take dynamic environmental light into consideration. So when environmental light changes, the system fails to estimate reflectance correctly. To estimate reflectance and environmental light at the same time, two equations are required to estimate two unknown values. Our idea to obtain two equations is creating two light conditions by switching projection at very high speed that human hardware perceives returning. By capturing two kinds of projection separately by camera, we can obtain a pair of simultaneous equations. To implement the idea, we create projector camera system using 3D projector, two cameras, and liquid crystal shutter filter, as known as 3D glasses. 3D projector projects L left image, R image alternately in very high speed. And we set L image as a projection image for appearance control. And we set R image as black image. Then the main camera with liquid crystal shutter filter L capture the reflected light of projection and environmental light. In contrast, the second camera with liquid crystal shutter filter R cut off the projection. So sub-camera only capture reflected light of environmental light. These two kinds of image are expressed with these two equations. This is our prototype system. We attach liquid crystal shutter filter to two cameras and displace them close to the 3D projector. And target objects are on the whiteboard, which is in front of this projector camera system. In addition, we used one more projector. For the experiment, we need to control environmental light artificially, so we loaded another projector for it. Using this experiment system, we did the experiment to confirm our method really can estimate reflectance robustly against dynamic environmental light. We prepared 3 light conditions for experiment. We control luminance of environmental light, color of environmental light, and both luminance and flow of environmental light. 3. Our system estimates the reflectance of object surface under these 3 environmental light, and we compare results with previous method. Here are estimated results when we change the luminance of environmental light. This first row is results of our method, and the others are results of previous method. To compare these images easily, I split these images and combine it to one image again. The results by our method look no bolder. However, we can easily find out boundaries in results by previous method. From this result, we can say our method is robustly against luminance change of environmental light. In second experiment, we changed the color saturation of orange-colored environmental light. The first row is results of our method, and second one are previous method. Let's compare them in the same way. We used orange environmental light, and we changed its color saturation from 0% to 100% gradually. In this slide, here are results under 0, 20, 60, and 100% saturation. Previous method cannot distinguish change of reflectance and environmental light, so estimated results by previous method become orange color when orange environmental light is projected on the project surface. But in our method, orange color does not appear in estimated results. In third experiment, we project the fourth image on this real object. So it's kind of extreme case. And these are the estimated results. The left images in each pair are results estimated by our method, and right images are estimated by previous method. This time we calculate the error between estimated results and round 2 and plot it as box 1. In all cases, there are significant difference between results by our method and previous method. We found 2 limitations in our method. First, the projector switches on and off in high speed, and it may lead flickering perception. To avoid it, we think 2 solutions. First, by tracking the object area and limiting the projection area to only this object area. This will be one solution, we think. And also, a more straightforward solution is using projector with higher frequency. One more limitation is maximum luminance of a projector. A 3D projector has left image and right image, and we set one of them as black image in our system. Thus, maximum luminance of a projector becomes hard. Because of lack of projection power, in some cases, it can be difficult to control the color. To solve this problem, we think we can set the pair of projection image, which the target projection color when the 2 images are mixed together. At last, we would like to show movies of controlled appearance. In these two movies, our system controlled appearance of the printed paper to black and white. The difference is effect to the environmental light. In left movie, the red flashlight is cancelled, and in right movie, red flashlight is changed to yellow light. Our system estimates reflectance and environmental light separately, so the system can control them also separately. Here's a summary. Thank you for listening.
Thank you for the nice presentation. The hardware solution and the concept look really interesting, I think. So, do you have any questions from the audience? Anybody? While I'm checking the Hoover QA. Okay, I think we have chat. I now can repeat this. Why do you use dynamically changing light instead of mixed light?
Dynamic.
Hello?
Yes.
So let me repeat the question, or you can just refer to the public chat currently. And so the question was, why do you use dynamically changing light instead of mixed light?
But I cannot get the
Question?
what mixed light is.
Okay, so yeah, the question is, okay, so why not arranging the light?
Arranging light.
Do you answer the question?
Yeah, I will answer the question. So the purpose of this research is to make this system make the applicability of this system wider. So we assume that environmental light is changing time by time every day. So we assume that environmental light is changing dynamically. So
For the question, Dorian. And so do you have any questions? So maybe meanwhile I have a question. So when I read your paper, okay, it's echoing. So, but yeah, I will just. So when I was reading your paper, I think it seems that you think the most limiting factor is the flickering that can reduce the user experience, and the key component to reduce such flickering is to use hardware with higher frame rates. That's correct, first of all. I assume it's yes.
yes.
So what about the software side? So do you also need to speed up the software, or can you just keep your current system or the software as it is and use the mean values, for example, of multiple frames to process the image?
Yeah.
Did you get my question? Oh, okay.
Yeah, I can get your question. The projector is projecting the image in 120 Hz, and it is not depends on our speed of the software. So I don't think the speed up of our software will decrease the recurring perception or something like that.
Okay, so yeah, thank you for answering the question. So I think we are already in time, and so thanks to the speaker again. Will?
You
So let's move on to the next presentation, which is transitioning 360 content-aware and field of view virtual camera paths for 360 video playback, presented by Miao Wang, Yiyun Li, Wen Shan Chan, Christian Wichert, Min Hu, and the presenter will be Yiyun Li. Sorry for my bad pronunciation.
Hello everyone, I'm Yijun Li from Beihang University. Today I'll introduce you transitioning 360 content-aware normal field of view virtual camera passes for 360-degree video playback. Contributes to the increasing number of 360 videos and images on the internet. Because of the low resolution, heavy weight, and the high price of head-mounted display, the majority of users tend to watch 360 video on 2D displays, like personal computers or mobile phones. The left figure shows one of the portable 360 cameras, and the right one shows the experience of watching 360 video on YouTube. In this traditional interaction mode, users usually need to use the mouse or touch screen to frequently change the current view content, which is tedious and inconvenient. Other than that, it is easy for users to miss the important objects outside the field of view. To solve this problem, previous work mainly focuses on computing single normal field of view camera paths to track important objects in 360 video automatically. For example, the method paneled to densely sample spatial temporal glimpse for every 5 seconds, where each glimpse is rated with a capture worthiness score. Then a virtual camera trajectory is constructed by maximizing the accumulated score. The final normal field of view video is rendered by cropping the view along the path. As for the 360 pilot, it uses an object detector to propose candidate bounding boxes and uses an RNN-based selector to filter the optimal bounding box. Finally, it uses an RNN-based regressor to learn smooth transitions between selected bounding boxes and renders the final result. These two methods aim to extract single normal field of view video without considering the interaction between users and the 360 video. To support interaction, Chang and Cho proposed an interactive and automatic navigation system computing the camera path in the following 3 steps. Firstly, it calculates an initial path considering pixel-wise saliency and camera smoothness based on optical flow in the scene. Then it performs field of view aware path planning to adjust the view using regional saliency. And finally, it performs temporal smoothing for the path. But the above 3 methods only compute one single camera path for navigation. Users will be unaware of the important objects outside the current field of view. In outside-in methods, the candidate off-screen content is visualized by creating off-screen view thumbnails that are floating on the screen. However, the off-screen content is manually labeled and fixed at constant position, which does not extend to complex and dynamic scenes. Therefore, we propose transition 360, a new technique for 360 video navigation and playback on 2D normal field of view displays. Given a 360 video and the number of normal field of view camera passes, our method computes the camera passes by considering content awareness and diversity and renders the normal field of view content to the thumbnails. Users can switch between them by pressing direction keys or clicking thumbnails. Our method follows 5 principles. At first, the content recommended to users should be the most interesting one in 360 video. When users are watching the main normal field of view video, they should also be aware of the off-screen important content by referring to the candidate normal field of view thumbnails. Furthermore, virtual cameras are required to record different parts which share the minimal overlap. And the content users are watching should be stable. The transition to other candidates' views should be smooth enough. Last but not least, the transition should be efficient and users won't get lost. Given a 360 video, our method computes the saliency, optical flow, and instance segmentation during preprocessing. The dynamic programming-based optimization algorithm with a core-to-find strategy is adopted to calculate the given number of camera passes. Finally, the results are shown in our user interfaces. The default video aspect ratio is 60:9. During preprocessing, in order to improve the computational efficiency, we uniformly resize the input video to a width of 360 pixels and set every 4 frames to 1 keyframe. Then the saliency, the optical flow, and the object segmentation maps are acquired by using the existing methods. First, let's consider how to compute a single camera pass. We just need to minimize this energy formula. The left term is for saliency and the right term is for velocity. PT represents a 2D pixel coordinate as a TSP frame. We can convert it to the formula below, which can be optimized recursively. It represents the energy of a pass from the first keyframe to the TSP frame ending at PT. For the TSP frame, we'll use the value to update the neighborhood at T+1 keyframe and record the best pass. It can be extended to multiple camera passes as shown on the right. We'll accumulate the energy of every camera and consider the interaction effect in the saliency term by using intersection over union for every 2 cameras. This animation shows the computation process of multiple camera passes. Please refer to our paper for more details. We offer 2 interaction interfaces. On the left, the candidate video thumbnails are shown horizontally below the main view. On the right, the candidate video thumbnails are floating on the main view by using outside-in method. Users can transition between contents by pressing direction keys or clicking thumbnails. We recruited 15 participants to evaluate. The results shows that our 2 interaction modes are better than others in locating capability, ease of use, and intention to use both in static scenes and dynamic scenes. Our method also has limitations. First, due to the limitation of memory, our method can process at most 4 camera passes. But according to our experiments, generally it is enough to cover the important parts in 360 video. Also, large number of cameras may lead to large overlap of field of view, which can degrade the view diversity. Second, the field of views of our cameras are fixed, which means if the tracked object is far away from the camera, it might be too small to observe the details. Finally, only saliency, optical flow, and incidence segmentations are used for content awareness in our method. If extra semantic information are considered like human-object interaction, it may improve the quality of content awareness. Here, we show more interaction examples. Thanks for watching.
Okay, thank you for the nice presentation. It looks really stable and promising. So do you have, from the audience, have any questions?
Yes, ladies and
Use the
gentlemen,
playback.
if you have any questions, just say it out. Yeah,
Yes.
I'm glad to answer your questions.
Okay, so meanwhile, probably I can start. So I think the for the edit rendering is now a hot topic in 360 videos or VR videos and rendering. And I think video method preferred views somehow needs to be rendered or decoded in addition to the centered view. So my question is, do you have any thoughts on how to combine for the edit rendering video method?
Yeah. Can you repeat it again? I didn't hear it clearly.
Okay, so I can make it short. So my question is, do you have any thoughts on how to combine or integrate for the edit rendering with your methods?
Yeah. I think it's a little bit tricky to combine our method because our method is aimed to be used in the 2D platforms like traditional screen or smartphone screens. Uh, yeah, I think it also can be used in the VR head-mounted displays, uh, like using the outside-in method. Uh, yes, maybe these floating thumbnails can be presented in the user's field of view, and the users can click these thumbnails to transition to uh, the interesting targets, and I think that would be an interesting idea of the implementation of in the virtual reality head-mounted displays. Thank you.
Okay, thank you. So does anybody have any questions from the audience? Ready? I think we can have one more question. Okay, so if not, I have one more question. So I think you applied your method to your VR video or 360 videos, but can you apply your method to AR content where, let's say, superimposed computer graphics will have some more important roles than the real ones? So do you need additional parameters to handle such content? Hello? Am I having some network troubles or something? Can you hear me, everybody? Oh, okay. Thanks. So probably you, Regine, is having some problems, I suppose. So I think it's now the time to move on to the next presentation. Oh, okay. So he's disappeared. So okay, so thank you for the presentation, presenter again, and let's move on to the next one. The next presentation is stage-wise Salient object detection in 360 omnidirectional image via object label semantic saliency ranking, presented by Guangxiao Ma, Xiaowei Li, Cheng Li Zhao Chen, Aimin Huao Hongji. So this will be presented by Yang Xiao. Okay, so please go ahead.
Hello everyone, my name is Guangxiao Ma from Beihang University. The title of my presentation is Stage-wise Salient Object Detection in 360-degree omnidirectional image with object level semantical saliency ranking. In recent years, many saliency detections for traditional 2D image has been proposed. However, there are few saliency detection methods for 360-degree image. What restricts the 360 degrees silent object detection? The first reason is visual deformation. The visual distortions usually results in large feature gap between 360 degrees images and 2D images. So traditional 2D saliency detection models can't handle these deformations. We try to use the most advanced 2D silent object detection model to detect silent objects in 360-degree images. As shown in the slide, due to the extension of deformation, there are more field detect areas. The second reason is the large problem domain. 360-degree images has large size and more objects than traditional 2D images, which lead to the expansion of the problem domain of silent object detection. The last reason is field distance. Traditional 2D silent object detection and fixation silent object detection datasets are numerous. However, according to our statistics, there are so far only 2 datasets for 360-degree silent object detection, with a total of only 607 images and both proposed in 2020. To solve those problems, we propose a multi-stage method for 360-degree silency detection using semantic ranking, and propose a novel new 360-degree silent object detection dataset, which contains 1,105 images and the semantical level. Our method is divided into 2 stages. The first stage is called level silence viewpoints localization, and the second is fine level silence objects localization. The 2 stages are similar. Each of our stages is composed of a ternary classifier C and the prediction unit P. The difference is that there is a viewpoint adjustment module after the first stage and a pixel-wise silency refinement module SR after the second stage. Given a 360-degree image, first detects all object proposal in it. Each proposal retrieves our similar proposal and make an object proposal pair. All object proposal pairs are fit into ternary classifier C1, and the silency scores are output. We show the detailed network on slides, where the deep feature for each input objects comprise 2 scales, the local and the global patches. in which the only difference is that the global cache G is 15% larger in size than the local 1L. By using the pre-trained VGG16 as the future backbone, the multi-scalar 8192 symmetrical semantical deep features of the input object A can be obtained by concatenating to 4096 symmetrical deep features that are respectively computed from its local and global observation VGGAL and VGGAG. Then there are two 8192 symmetrical deep features, which are respectively related to the two input objects, will be future fit into a full connectation network. And the error backpropagation procedure will be get via Hankelos. We rank all objects in descending order according to their silency values. The top 5 objects will be used as the initial candidates. Then we learn a prediction unit P1 as a typical SVM. The P1 is to determine how many objects among the candidates should be selected as the silence viewpoints. The production unit P1 takes a 5-4 symmetrical vectors as inputs, which include the object center coordinates, the area proportion of objects. Thus, the output of the P1 will range between 1 and 5. The production unit P1 also selects those proposals with high scores and converts those proposals into distortion-free viewpoints. The second stage is similar to the first one, and it's also composed of ternary classifier C2 and the production unit P2. But it should be noticed that what C2 and P2 deal with is the distortion-free proposal after the first stage procession, which will reduce the problem domain. After C2 and P2, we get many patches containing silent objects. We use a fine-tuned patch silent detection model to retain the silent objects pixel by pixel to obtain the final silencing map. In order to solve the problem of data shortage, we propose the novel 360-degree silent object detection dataset, named 360 SSOD, containing 10 kinds of segmentical labels and 1,105 images. The reason for considering semantical labels is that in the previous 360-degree silencing detection dataset, a large number of marked silence objects were present, and other objects were less marked, which resulted in the feature of many silent objects could not be learned by the model. Our novel dataset uses a pixel-by-pixel annotating method for multiple people in each image to mark silent objects. We compare our ground truth with the fixation ground truth, and we can find our ground truth in line with human vision. It also corrects some mistakes in the fixation ground truth. For example, the red box inside actually a non-silencing object. This is the experiment of our method. It can be seen that our method and ground truth have almost similar object contours, while other methods either lose silence objects or have detection errors. This is the result of our quantity analysis. It can be seen that our method is more than 10% ahead of other methods in almost all indicators. So, in conclusion, we have developed a novel multi-stage silent object detection method for 360-degree images, which can outperform all previous approaches significantly. We have proposed the semantic silencing to handle various zero distortions in 360 omnidirectional images. We have constructed a novel dataset, 360 SSOD, containing 1,105 360-degree omnidirectional images with pixel-wide saliency normative. To the best of our knowledge, this is the largest dataset for the 360-degree silence object detection problem. Thank you for your attention.
For the presentation. I suppose Zenta is still having a microphone problem, so to the audience from the on YouTube channel, I think it's just they cannot see the public channel chat, so I will just read the question from the public chat, speak out loud, and then to just tell what is happening. Okay, so we have one question from Xing Yao Yu, and the question is semantically balanced. Does that mean that the amount of the pictures with different semantics are the same? Okay, so he's answering, yes, it is almost the same. Okay. Do you have any other questions from the audience? So actually, I have a question from the audience of the YouTube channel who is privately contacting me, and the question is: so if the 360 degrees of your 360 camera rotates, and then the vertical axis, let's say, lean to some other axis, and then so do you still get the same result? Okay, so I can type it in as well. So if you, so it's written in other languages. So I'm just, simultaneously translating and questioning. And so if your 360 camera rotates, and if it changes the axis, the vertical axis, for example, and then do you still get the same result? So if your 360 camera rotates when you're capturing the video, and then it changes the vertical axis, I suppose, and then do you still get the same result? The intention of the question is that, if the CNN is trained for a specific images which is taken in a stationary camera, and then if the axis rotates, and then I think it is somehow biased, right? I mean, the result will get some different result, or is this? So probably I can rephrase this like, so is your method robust enough to handle the rotating cameras? Okay, so yeah, he's typing. Okay, so he's answering like, we considered a fixed angle camera and did not consider rotation. So yeah, probably we will have some artifacts probably. So I have one question. And so I think in the probably I can just copy and paste mine here. So my question is, the saliency ground truth images look like binary object masks, mask images, but is there any differences between your ground truth saliency maps and the conventional saliency maps? So if I understand it correctly, the saliency map usually have some gradients in it, like not like the binary mask, like 0 and 1, but it has some gradients in the grayscale images from varying from 0 to 1. Typing now. Okay, so probably we are short in time, so maybe we can continue this discussion after this session. Okay, so thank you everyone for the active discussions on the chat and course, and so thank you again to all the speakers. And we are closing now. Thank you.